Disclaimer cause all materials in this video are for educational purpose only.
I bought an internet camera called a Welcome and installed it in my house. It used machine learning to recognize the faces of people coming in the front door. It would figure out if someone new showed up and alert me on my phone. I thought it was really neat, and I loved that it was doing machine learning right in my living room. But when the camera eventually stopped working, I didn't bother to fix it or replace it. And here's why. My teenage daughter didn't like that the camera was watching her, and she hated that it was keeping a video record of her arrivals and departures. This example exemplifies a really important issue in machine learning. Machine learning algorithms need to look at our data to do anything interesting for us, but that means they need to look at our data. During the first 2 decades of the 21st century, large-scale collection, processing, and retention of personal data became pervasive and increasingly invasive. Yes, employing this kind of data benefits science, engineering, and medicine, but so much private data being gathered in so many ways raises real risks for misuse, including harassment, discrimination, and even crime. In short, machine learning can and does put our privacy at risk. But in this lecture, we'll look at 2 specific techniques that are being developed for mitigating these risks. Homomorphic encryption hides private data in plain sight, so machine learning algorithms can be applied to the data without revealing its contents to the organization doing the machine learning. By contrast, differential privacy is a technique that blurs the personal data before training machine learning models, another way to prevent it from being extracted and exposed. To understand where privacy can be violated, consider a very simple machine learning pipeline. In this example, personal health information is being collected by a hospital. The hospital is a relatively trusted organization governed by privacy laws, and users are willing to share their data in exchange for medical care. To evaluate possible cures for diseases and improve patient care, the hospital wants to run sophisticated machine learning algorithms on the data. That's not something people running a hospital have typically been well equipped to do on their own. They don't have the algorithms or the processing power to do state-of-the-art machine learning. That's something that some other organization, some kind of cloud-based machine learning service, would be better suited to do. Because of privacy legislation, the hospital can't just hand over the private patient data to the machine learning service. At the very least, all identifying information in the training data needs to be removed. So names and addresses need to be taken out. Often even zip codes need to be removed, since any non-local person using the hospital from out of the area would be easy to identify. The cloud-based machine learning service runs on the de-identified data and produces a trained network. That network can be used for making predictions on new patients. If everyone involved is trusted, this pipeline makes sense. It lets each organization do what it does best, and it provides the service of making medical predictions. That's valuable to patients and their doctors. But in the context of untrusted parties, what computer security experts sometimes call adversaries, this machine learning pipeline has risks. In fact, there are multiple ways that personal information about individuals in the dataset can be revealed or leaked to untrusted parties. The first place where an individual's information can leak is if the hospital's health data gets hacked. Hackers have a long history of seeking and getting large amounts of sensitive information. Banks, at least one credit reporting agency, email providers, social networks, and hotels have been the targets of high-profile hacks that have exposed billions of user accounts. Fortunately, hospitals are held to a very high security standard with a decades-old culture of protecting private information. And laws such as Europe's 2018 General Data Protection Regulations and California's 2020 Consumer Privacy Act are forcing other sectors to protect personal data more like hospitals do. But machine learning is subject to other kinds of leaks that require more specific methods to protect private information in the machine learning pipeline. In particular, even de-identified data can be a target for attack, a lesson the machine learning community has learned the hard way. As we discussed in Lecture 12 on recommender systems, the 2006 Netflix prize ended with a privacy lawsuit. Netflix had released a dataset with movie ratings from 500,000 users and offered researchers a $1 million prize for using the data to improve accuracy at predicting movie preferences. And Netflix had de-identified all the user data. People's names were removed. But researchers correlated the preferences expressed in the Netflix data with preferences already available online, like publicly posted movie reviews by individuals on IMDb, the Internet Movie Database. They found that if you can use online reviews to identify just a couple of obscure movies that someone has seen, then you can figure out who they are in the Netflix data. Also in 2006, a similar vulnerability was discovered in AOL's public release of de-identified data to researchers. The experiences at Netflix and AOL led tech companies to become much more wary about sharing even de-identified data with the public. And after Facebook's collaboration with Cambridge Analytica resulted in a major data breach in 2016, even behind-the-scenes research became a focus of concern. So, what to do? A powerful tool from computer security that can help avoid leakage of data, whether de-identified or not, is encryption. If cloud-based machine learning services would store their data in encrypted form, only someone with the decryption password would be able to read the data. Even better, if the data source, such as the hospital, encrypts the data before sharing it with the cloud service, the chances of exposing sensitive information go way down. But if the hospital encrypts the data before sending it to the machine learning service, we can't expect the service to be able to do machine learning on the data. It's a catch-22. However, there is an amazing approach for making it so that encrypted data can be used for learning. Although it's not yet practical to deploy at large scale in 2020, it's a very promising idea that's worth sharing. From the hospital's point of view, the basic puzzle is, how could the service do computation on the hospital's data without, well, looking at the data? Here's a simple way the hospital can get the cloud-based service to do valuable work for them without exposing the sensitive data. Decoys. Decoys are often used in movies as a way of obscuring sensitive information. For example, let's say a jeweler has a priceless diamond necklace and needs to transport it from store A to store B. The jewelers know that if they simply drive the jewels from A to B, thieves would be watching and they would deploy a crack team via helicopter to the location of the car, stop the car, and steal the jewels. So the jewelers get a great idea. They will take 2 identical briefcases and load each into one of 2 identical cars. Then drive the cars on 2 entirely different routes. The thieves are watching all of this, so they know what's happening, but they can't be sure of where to deploy their team. If they just pick one of the cars at random, there's a 50-50 chance of getting nothing at all. To apply the idea of decoys to the machine learning privacy problem, the hospital would prepare a second data set consisting of fake data. Then, they would ask the service to do learning on both the real data and the fake data. This way, the service isn't sure which data set contains the sensitive information and which data set contains made-up nonsense. And the more decoys the hospital creates, the more secure the data is. If the jeweler sent out a fleet of 128 identical cars, they could start to feel pretty confident that their delivery would get through without the real jewels being intercepted. In the hospital case, that would mean asking the service to train on 128 different data sets. Most of that computation isn't directly being put to use. Instead, it's just there as a distraction. So training with decoys becomes more private, but also much less efficient in terms of time, storage, and electricity. And this trade-off is especially important to keep in mind, because in the digital world, even 128 decoys may offer only a modest level of protection. Ideal privacy would use a lot of decoys. Fortunately, there's a scheme for doing calculations with 128 decoys that produces the equivalent of 2 to the 128 decoys. The idea, called homomorphic encryption, is that each bit of the data is delivered to the training algorithm in 128-bit encrypted form. The encryption is designed so that the basic operations we need for machine learning, things like multiplying and adding vectors, can be applied to these encrypted values in a way that produces other encrypted values. These encrypted values, when decrypted, produce the same answer as if the analogous operations had been performed directly on the original data. In mathematics, this kind of analogy is called a homomorphism. In this instance, the analogy is between computational operations on unencrypted data and analogous operations on encrypted data. If the analogy is well formulated, the results of operations on the encrypted data will continue to match the operations on unencrypted data. That's why this kind of decoy-based encryption is called homomorphic encryption. Visually, you can think of homomorphic encryption as supporting computational operations on encrypted data. Say we want to use a homomorphic encryption service to add 3 and 2. We'd encrypt the 3 and the 2 and send them to the service. The encrypted values can be thought of as including the 3 and the 2, but also many, many decoy values at the same time. Then we'd ask the service to add those numbers. The actual operation that the service would execute is not addition, but something that carries out an analogous, in other words homomorphic, version of addition on the encrypted numbers. It's essentially doing the operation on all the decoys simultaneously. The service would send us back the results in encrypted form. When we decrypt it, lo and behold, we discover that the answer is 5. The service does the calculation for us, but never learns our numbers. Even the answer it provides is just one piece of hay in a haystack, given the many possible problems we might have been asking it to solve. As an approach for keeping the training data away from prying eyes, homomorphic encryption seems right on the edge of viability as of 2020. Proposals existed for privacy-preserving versions of linear regression, logistic regression, decision trees, k-means clustering, SVM classification, and neural networks. And researchers are continuing to discover more efficient operations for carrying out key steps of machine learning algorithms. If we keep our original data safe and protect even de-identified data, it can be very tempting to think that there's nothing more we need to do with regard to privacy in machine learning. But in fact, even the trained model itself can leak private information. Researchers have shown that it is possible for attackers to coax specific training instances out of workhorse models we've seen, including deep networks and support vector machines, especially if partial information about the training instances can be discovered by the attackers. Let's look at one specific example in detail. We'll see how private information can be extracted from a trained model, and we'll examine an approach to differential privacy that is effective at hiding the private information. We'll be trading off some immediate utility of the trained model in favor of more privacy. First, let's be precise about the scenario we're studying. Computer security researchers call a security scenario in which the attacker has some information and seeks to leverage it to reveal other information a threat model. We've hinted at a few threat models already. The specific threat model we'll examine now is one where an attacker, Eve, has access to 2 trained models produced by a known machine learning algorithm, naive Bayes. One is trained on a set of data that includes your private information. The other is trained on the same set of data, but without your private information. Now Eve, the attacker, is in an ideal position. She can leverage all the information she has to uncover specific private information that is specific to you. The situation roughly corresponds to what happens if you demand to have yourself removed from a known database. An attacker might compare the known database before and after your information is removed and use just this information to figure out your private information. It's also a great test case for privacy. If we can protect your data even here, we protect it in lots of more realistic scenarios. We'll look at the case where Eve, the attacker, cannot directly access the trained model, but she can issue queries with specific instances to see how the model classifies these instances. So here's how the adversary Eve can figure out the missing training instance given access to a trained naive Bayes classifier. Eve can see a dataset consisting of instances where each instance is a vector of numbers. Each instance is labeled as white for negative or gray for positive. One instance is hidden behind a black bar. Eve can see the trained model. In naive Bayes, the trained model consists of the probability of a 1 in each position amongst the positive examples, and the probability of a 1 in each position amongst the negative examples. The trained model also includes the prior probability of an instance being positive or negative, which is computed by counting the number of positive examples, the number of negative examples, and then dividing by the total number of examples. Here, we can see 5 positive and 5 negative examples in the training set. How can we figure out the label of the instance hidden behind the black bar? Well, if it were negative, the training set would consist of 6 negative and 5 positive instances, so the prior for negative would be 6 out of 11 positive, or roughly 0.55 for negative examples, and 5 out of 11, or 0.45, for positive examples. Like Eve the attacker, we observe that it's exactly the reverse, with a prior of 0.45 for negative examples in white and 0.55 for positive examples in gray. That means the label of the missing example is more likely to be positive, gray. That's very valuable information for Eve the attacker, who can now focus her attention exclusively on the positive cases. This narrowing in is possible with naive Bayes because the positive model depends only on the positive instances in the training set, while the negative model depends only on the negative instances. All Eve needs to do is solve some simple algebra problems for each column. The first column consists of 3 zeros, 2 ones, and 1 unknown value. The average of the 6 values is roughly 0.5. That means 3 times 0 plus 2 times 1 plus x equals 0.5 times 6, or 2 plus x equals 3. That means x must be 1. For the second column, the same reasoning gives us x equal to 0.18. That doesn't quite make sense, since x should really only be 0 or 1. But the values in the model are rounded to 1 decimal place, so that suggests that x needs to be rounded too. The missing value in the second column is 0. Column by column, Eve pieces together the values in the missing instance. In short, an attacker can gain private information by using knowledge about the training procedure and the internals of the learned model. Sometimes, even ordinary access to a public query interface of a trained classification model can be enough to break privacy. If people can use the trained model to make predictions, they can learn about the data that was used to train it. That means such a public interface has a much larger number of potential adversaries. These adversaries don't have to figure out how to force their way in to steal the data. They merely have to figure out a clever way to play this particular form of 20 questions until something private gets revealed. Let's return to the example at the beginning of the lesson and look at a dataset with pictures. The pictures to protect might be snapshots of faces from my home that my daughter does not want shared. But here, we'll use personal items of clothing to stand in for personal images. We'll train a naive Bayes classifier to distinguish 2 classes in the fashion MNIST dataset, t-shirts and sneakers. This first block of code prepares the dataset. Train X, Train Y, Test X, and Test Y are the full set of training and testing examples from the dataset, where X represents the instances and Y the labels. The instances are arranged as 28 by 28 grayscale images. For training the model, we'll reshape the data into flat vectors of size 784. To simplify training, we'll convert the grayscale images to black and white. For each image in the training and testing set, we compute the median grayscale value and call everything below that value 0 and everything above that value 1. The fashion MNIST dataset includes 10 classes, but we're only using class 0, which are t-shirts, and class 7, which are sneakers. Test Y pair, Test X pair, Train Y pair, and Train X pair are subsets of the training and testing data where only the pair of target classes are retained. The dataset includes 12,000 training examples and 2,000 testing examples, evenly split across the 2 categories. Before we start training on this data, let's take a look at it. To see the image data for ourselves, we can take the flat vectors and turn them into 28 by 28 arrays again, then use Keris's image library to display them as grayscale images. The function showPic takes a flat vector and displays it. It scales the images from their 0, 1 black-white values to 0 to 255 pixel values for display. We loop through the first 10 examples in our training set and display each one. Because of the conversion to black and white, the images appear mainly as silhouettes. Nevertheless, it's enough to show us which items are t-shirts and which are footwear, and even some distinguishing markings. Let's train a naive Bayes classifier on the dataset we've prepared. GNB is the naive Bayes classifier on continuous values, which the scikit-learn library calls Gaussian NB. We fit the classifier using the training data, then use the resulting model to make predictions on the testing instances. The predictions, pred y pair, are compared to the labeled testing instances, test y pair, to compute an accuracy. The trained classifier only gets 3 wrong out of 2,000 testing instances. So far, so good. The learned classifier achieves 99.8% accuracy on this dataset. Next, we'll prepare a new dataset consisting of the same instances, but with one instance arbitrarily selected for removal. We'll set remove to be the position in the dataset for the instance we'll be removing. Then we'll save the instance and its label so we can refer to it later. Eve the attacker doesn't have this information, but once she reconstructs the missing instance, we'll want to see if she was successful in her attack. Train X pair 2 and train Y pair 2 are the new training set. We'll train up a new classifier, see what it predicts on the testing data, and evaluate it. Removing this one item from the training examples doesn't change the classifier much. After all, there are 19,999 other examples. The number of mislabeled points at 3 remain the same. Now it's time to try to play the adversarial role of Eve the attacker and extract the missing instance from the model. In the privacy literature, attack strategies are published as a proof that an existing approach to security is insufficient. Here's a strategy Eve might take to extract information from the trained naive Bayes classifier. When Eve begins the attack, she has access to 2 trained models. One model is trained including the private instance, and one is trained without. All Eve can do is query the 2 models with different inputs. Eve can proceed by constructing a synthetic instance that the trained model classifies as roughly 50% t-shirts and 50% sneakers. She looks to see how each of the 2 models classifies the test instance. In one case, she asks the original model. In the other case, she asks the model trained without the target data item. Then, for each column, she temporarily puts a 1 in that column of the test instance. She asks both the original model and the new model to classify this instance and notes which one reacts more strongly to the change by changing its class prediction. The reconstruction of the image is exactly the pattern of which components cause more of a reaction in the original model or the retrained model. For example, we can probe each pixel of the image and see which model responds more. We'll color pixels gray, where the original trained model responds more, and blue, where the newly trained model responds more. The resulting image will be an approximation of the private image that was removed from the dataset. It's a t-shirt. All right, let's actually try this attack. Eve the attacker has access to 2 classifiers, one with our private image, one without. She queries each one to build up a guess of what the private image was. I ran Eve's strategy a half dozen times with different missing images. The trained classifier has evidence of a lot of the details of the images it was trained on. You can make out some distinguishing patterns on the shoes and the t-shirts. Keep in mind that Eve the attacker made these pictures just by querying the 2 models a small number of times. That was enough to extract and reconstruct the target image out of the 2,000 images it was trained on.
Thanks for watching this video. If you like this video, please click like. If you want to subscribe, please click subscribe. Please be subscribed. If you want to click the bell, please click the bell. Thanks again.